Now we are going to start number 718, which is a precipitation titration example and problem you did in your homework. So the question is actually on the board. So it asks for the titration of a certain amount of Ki with that concentration, and you are titrating with this amount of silver nitrate, and it asks you to calculate PAg plus with the following volumes. So the first thing that we have, even before we even start this problem, is look at what is the titrant and what is the analyte, okay? And then this gives us a sense of what our titration curve is going to look like. So first off, titrant and analyte. Titrant and analyte. So in this case, it says you're titrating, you have 25.00 milliliters, and you're titrating with silver nitrate. So if you're titrating with silver nitrate, that is what is in your burette. So if that's in your burette, then that is what your titrant is. So this is your silver nitrate. Hence, your analyte. Your analyte is going to be your Ki solution. So which of those is going to be reacting with your silver nitrate? In this case, it's going to be the iodide. And so your analyte for this one is going to be iodide. Because, remember, we're looking at precipitation and titration. So to look at this reaction, we have Ag plus iodide, I minus, giving us Ai plus AgI solid. Okay, so we already said that this is our titrant, this is our analyte. Okay, so the first thing we're going to have to know is we can already give a rough sketch of what this should be expected to look like. We already know that if we made a titration curve, then on the x-axis we have the volume of the titrant, usually in milliliters. That's what's coming from our burette. So we know the volume of our titrant in milliliters is going to go here. And then we have our concentration of our titrant. So the concentration, and instead of just concentration, we actually take PAg plus. And remember, PAg plus is equal to negative log of the concentration of the Ag plus ions. Okay, so that's what we'll be plotting if you were going to make the entire curve. And then, so this is your concentration, and what you should see is a reverse S curve, okay? So you'll see this is this area is known as your pre-equivalence point. Pre-equivalence point, before it reaches this equivalence point, the equivalence point is here. I'm denoting that as EP, equivalence point. And then we have another region, which is our post-equivalence point. Okay, so equivalence point, remember, look back at your notes if you're unsure what it is, but the equivalence point is when you have equal amounts of your titrant and your analyte. Okay, so you have equal amounts of both, so that everything is shifted to the right. Okay, so you have both of these are completely consumed, and you're forming AgI solid. Okay, so that's at our equivalence point. At our pre-equivalence point, what we have is we are limited by the amount of titrant we have. So we have excess analyte. So in this case, we have excess analyte. And in the post-equivalence point, we have excess titrant. So we're going to have a higher concentration of Ag+, hence also a lower pAg+. Because if we have a lower P, even in the case of, say, pH, if it's a lower pH, we have a higher concentration of H+ ions. Same idea for silver. If we have a low pAg+, then we have a high concentration of that Ag+ in our solutions. Okay, so let's go back to the question at hand. So it asks us for this pAg+ at 3 different volumes. The very first thing that we are going to have to do is identify what the volume is at the equivalence point, and that's our V sub E. Okay, so our V sub E, remember I said that it is when we have the equal amount of moles of your titrant and your analyte. So let's find what that volume would be if we have equal amount of moles. So we need to get to moles first. So we know how much analyte we have, so let's find the moles of analyte. And then we also have the concentration of our titrant, so from that we can also get our volume. Okay, follow me through this problem here. So we know how much analyte we have, so we have 25 milliliters and at the concentration above. So let's convert to liters first. I'm not going to show it here because I assume that you can get to liters, but you're going to get to moles of your analyte. So you are going to start with 0.02500. This is liters of iodide. Then you are going to multiply it by the concentration. We have 0.08230 moles of iodide per 1 liter, so liters cancel out. Now we have moles of iodide. We know that there is a 1-to-1 mole ratio of our analyte to our titrant, so we are going to state that here. So we have 1 mole of iodide to 1 mole of silver plus. And then the last thing that we need to find is, remember, we want to find the volume at the equivalence point. So the volume is going to be determined by the concentration that we have. And the concentration is given as well, and that's 0.05110 molar. So we have moles on the bottom, so we are going to write the concentration here as shown. That's moles of Ag plus over 1 liter, so moles of Ag plus, so this is going to be of our liters of our titrant. And that is going to be, we can get it back to milliliters. So we have our volume times our concentration of our analyte here, of our analyte solution. Then we look at the molar ratio, so 1-to-1, so we don't have to worry about this, and we divide by the concentration of our silver or our titrant solution. So then the number of milliliters that you should get is 40.26 milliliters, and this is equal to V sub E. Okay, good. So now, we haven't even answered any of the questions yet, but we are on our way to answering the first part here. So part A, now we got to calculate the P silver nitrate, or silver, PAG+. Okay, let's get to that. So remember, I said that the pre-equivalence point is where we have excess analyte. So what we're going to do, if we have excess analyte, then we would consume all the titrant. Okay, so if we were going to just look at it superficially, we would assume there'd be 0 because all of it would be consumed. In fact, there's a little bit that comes back. So even though we say, okay, all of it's consumed going to our products here, some of it will go back because of our equilibrium, our pesky solubility equilibrium. So remember that. So we have some AgI plus that goes back and forms the silver ion again. So it's going to be a very little concentration, but there's just that little bit that comes back. So that little bit that comes back because of this equilibrium is what we want to measure. Now, so we still have, so we don't need to know the solid, but we can look at what is this equilibrium. So we're going to assume, because we're in chapter 7, we are not going to use activities for this one, because that comes in chapter 8. For this one, we are assuming that the activity coefficients are 1, okay? But our KSP is equal to our AG plus and our I minus, okay? So now if these were equal, then if we were at equilibrium, then I can say, okay, well, I can find my equilibrium constant, and then both of these are unknowns. They're going to be the same value because it's a 1-to-1 ratio. So then we can find respectively what these are. The problem is we actually have more iodide. So we have to find that concentration of iodide first. We have no KSP, and then hence we would then solve for Ag plus to find what that concentration is, okay? So what this next process does is we're finding how much excess iodine there is that will be present, that concentration, and then we're going to solve for the silver plus. So how do we find this I minus first? And we're doing part A. I minus. So remember, some is going to be consumed with our titrant that we added, and we started with a certain amount, which was given in the beginning. So we want to find the total that we started in the beginning. We want to see how much was consumed with the silver that was added, and then whatever's left over is going to be the moles that we started with minus the moles of silver added. It's going to be how much is left over. So let's do this math out. So remember, I just said this is the moles of the originally subtracted by the moles added will give you our, and this is our remaining. Okay, so the moles we can get from the concentration times the volume in liters. So we have 0.0250 liters times our concentration, which is 0.8230 molar, minus the moles of silver added. And so in this case, we added 39 milliliters, or 0.03900 liters, times, in this case, the concentration molar. And then this gives you 0.0025 0575 minus 0.00199 subscript 9. Sorry, this is a 9, not a G, a 9. And then the number of moles that remains is 0.00006 or subscript moles of iodide. And now, so you have these moles here, and I need to get in concentration now. So to get in concentration, we can divide by the total volume that we have, which is the initial volume that we started with plus our 39.00 milliliters, and we're going to convert that. We're going to have that in liters, and that'll be our concentration. Okay, so we're almost done. We're getting there. Okay, so we have our moles, and we want concentration. So what we're going to do is we are going to go here, and we are going to divide by the total volume, which is 0.2500 That's what we started with here. And then liters plus what we added, which is 39.00 milliliters, and I'm going to convert that to liters. So that's our volume, so now we have moles per liter, and the concentration that we will get, that you will get, is 1.0 subscript 1 10 to the negative third molar, and that's for our iodide. Okay, well we have the iodide concentration. Now let's plug this in back over here, and I'm running out of board space, but I will complete this problem, this part of the problem, and you'll see in the next video we'll do B and C. So here we have our KSP equals our AG plus, so that's what we're looking for. And actually the KSP, recall you can look that up. It's in Appendix F in your book, F for Frank, and the KSP is given as 8.3 times 10 to the minus 17 equals our silver plus times our iodide concentration 10 to the minus 3 molar. Then your silver ion concentration will be 8.2 subscript 5 times 10 to the minus 4 molar. Oops, minus 14. Sorry, I read the number wrong. 14 molar. So that's our silver ion concentration. Now I want the PAG plus, and the PAG plus is equal to negative log of your 8.2 subscript 5 times 10 to the minus 14 molar, which equals 13, and we have two significant figures here. Remember, the first two do not count for significant figures when we're looking at logs. So it'll be 13.08. Okay, so if you cannot see it, it's 13.08, and that is in the very top part of this curve here. Okay, so again, it's a pre-equivalence point, and the next video will have part B and C.